Welcome. This talk presents an approach for training neural networks under constraints. In particular, we want to make sure that certain desirable properties are preserved when we train with stochastic optimizers. In a nutshell, we achieve this by a reparametrization trick. Instead of directly optimizing the network parameters, we instead optimize perturbations to these parameters. This is useful because preserving properties under a perturbation is often much easier than generating feasible parameters from scratch. But first, let's think about some properties that we might be interested in. If we're lucky, we can directly encode them in the network design. For example, to restrain the output to a certain interval, we just append a sigmoid to the network. Or if we want to reduce the intrinsic dimensionality, we can use a low-dimensional latent space as an autoencoders. But for other properties, this is not always so simple. Take, for example, physical symmetries or invertibility. Making sure that the network obeys such properties during training can be very challenging. In this work, we are primarily interested in training linear layers that we can easily invert and compute their determinant. This is because we want to use them in the context of normalizing flows, where both these properties are crucial. So how can we train invertible matrices? Previously, others have used orthogonal matrices as their inverse and determinant are easy to compute, but this is still quite restrictive. Instead, we want to be able to generate arbitrary invertible matrices, and here's how this works. Let's say we initialize the weights with a matrix for which we know the inverse and determinant. Then we train two vectors u and v, which form a rank 1 perturbation. Through these two equations, the Sherman-Morrison formula and the matrix determinant lemma, we can cheaply compute the inverse and determinant of the perturbed matrix. Now, let's put this into practice. We first initialize our linear layer with a matrix for which we know the inverse and determinant, but we will freeze this matrix for the optimizer. Then we initialize the rank 1 perturbation as the identity. We can do this by setting one of the vectors to 0 and randomizing the other one. Next, we then minimize the loss function with respect to u and v using the perturbed network. After a couple of such minimization steps, we merge the optimized perturbation. This means that we update the frozen parameters, reset the perturbation to the identity, and start from above. The advantage of this stepwise scheme is that we can, at all times, cheaply evaluate the inverse and determinant. Further, after a number of merging steps, the matrix A can approximate any arbitrary invertible matrix. Let's check out a few examples. First, we stack these invertible layers with bijective activation functions to form normalizing flows. Then we use these flows to approximate 2D distributions. The samples closely follow the ground truth distribution. This is in contrast to real MVP layers, which are not able to separate the modes cleanly. Next, we set up a Boltzmann generator composed of real MVP blocks and invertible linear layers. We use this generator to sample conformations of a small molecule, alanine dipeptide. This is a hard test case, since the ground truth energy is very sensitive to small displacements. In contrast, the samples from the Boltzmann generator match the ground truth Boltzmann distribution very well. Complicated features like the joint distribution of the backbone torsions are also closely matched. In summary, we present a new method for preserving network properties during training. We demonstrate this scheme for training invertible linear layers. These layers have tractable inverse and determinant and can approximate any well-conditioned matrix. For details, please check out our preprint, see the link in the description below, and thanks for watching.